Okay, this is the solution outline to the first assignment. The assignment problem contains two problems. The first one is basically a review of linear algebra quantities with MATLAB, but it is built on the same problem that we are going to do in the second problem as well, that deals with modeling a stagewise separation process. In the first problem, you're asked to write a function file that accepts two inputs s and n and produces a tridiagonal matrix of this form that you see here. So it must contain d's on the diagonal and then c's on the upper diagonal and a's on the lower diagonal. But these are told, like c is given as -1 for all entries, and a is given as -s for all entries, and d is given as 1 plus s for all entries. So we're going to have only s as an input and n as an input. So n represents the number of entries in the matrix. So for example, s equal to 1 and n equal to 4 would construct a 4 by 4 tridiagonal matrix. And then we will do a number of computations that basically review material that you would have seen in linear algebra, but using MATLAB as a tool. So how do I write the first function that I'm asked to do in part A? Okay, so I open up MATLAB and I have written the function already, and I'll just take you through the steps that are involved. So it is a function file, so it must have the keyword function, followed by the output t, followed by equal sign and some name of the function that you give, followed by the input arguments. In this case, we are told that these would be s and n. In the next several lines, we can put a lot of comments about what that function is supposed to do. So for example, I'm saying that it constructs a tridiagonal matrix, x is called the separation factor, and is the dimension of the matrix equal to the number of stages. And I also say how I'm going to calculate the lower part, the diagonal part, and the upper part. And these are actually given in the problem statement itself, that d is given as 1 plus s, a is given as -s, and c is given as -1. Okay, so that's just a comment to explain what I'm doing. And then I actually carry out the execution, that l is equal to -s, d is equal to 1 plus s, and u is equal to -1. The next line, the first line 8, is essentially an assignment, a set of assignment statements separated by a semicolon. I can actually stack any number of these statements. I could also write them one below the other if you are more comfortable with this. They are equivalent. The next line, line 11, is the key statement, because there are functions within functions that are written in a very compact way. For example, once n comma 1 will create a vector of dimension n by 1 containing only 1. If you want to verify that, you can go to MATLAB and see what it would do. For example, 4, 1 will create 4 rows and 1 column, just containing 1. And then I multiply that by d. Okay, and that's the one that's going to go on the diagonal. And this entry is then passed into the output from once n comma 1 is multiplied by d, and that becomes the input to the next function diag. Okay, and that produces the diagonal entries. For example, I can just verify that diag once 4 comma 1 multiplied by 5. For example, if d happens to be 5, then I can see what it does. So it produces a 4 by 4 matrix with 5 as the entries. Once you understand that part, the remaining are all essentially a repetition of the same thing. So I have a 4 by 4 matrix. To that, I want to add another matrix, 4 by 4 matrix, again creating ones, but this time with one less dimension, because the off diagonal element I have only 3, the diagonal is 4. So if the diagonal is n, the off diagonal must be n minus 1, and that is multiplied by l, so that's going to go to the lower diagonal part. And the diag function also takes a pointer which says where does it go. If you don't specify it, it goes on the diagonal. If you specify it as -1, it goes below the diagonal. If you specify it as +1, it goes above the diagonal. Okay, and that's basically constructs your tridiagonal matrix. Now, once having written that, you can save that function and test that function coming into the MATLAB window. So you can say, for example, TRID, which is the name of the function, and say 4, 1. So it says use S as 4 and construct, a 4 by 4 matrix. Okay, so there it is. So I know now it works. I can easily verify this for any other dimension, and it always produces a triagonal matrix that corresponds to what I've been asked to do. Now the next part of the question is, using this tridiagonal matrix, carry out all these computations, compute the determinant, compute the LU factor, compute the inverse, compute the rank of T, compute the eigenvalues, product of the eigenvalues, etc. So there are about 10 different parts that you are asked to do. Okay, the characteristic polynomial, for example, or the eigenvectors orthogonal. So you need to answer each one of them. How do we do that? One way of doing that is to write a script file. Okay, and that I've shown here. Okay, and the script file basically implements part by part. And here I'm going to show you something about report generation that we have not done so far. When you write a script file, remember a script file is any comment that you can enter from MATLAB command window, you can put it there. Now a % sign is a comment. But if you put 2% sign followed by exactly one space and then type something, that becomes kind of a demarcation of a cell. A cell is essentially a group of programs that you can execute by itself. So in the first 2 lines, I just have comments saying this is assignment 1, problem 1, review of MATLAB commands. Then I start a next cell. And all I have to do is put the 2% sign in the space. For example, if I remove that, see what happens. So it merged these 2 cells. Now I put them back, it divides them into 2 cells. So the way to create a new cell would be simply to start % space, and then you type whatever you want, and the commands that you enter in that cell can be executed as a standalone program. Okay, so now, for example, I want to execute this cell, which contains line 3 to line 6. I go to this icon and then evaluate cell. So I click it once, and what will happen is it would have executed line 3, 4, 5, and 6. And if there is any output that is to be produced, it would have been produced on the MATLAB command window. For example, it says type TRID in line 6, and the execution of that gives rise to the typing of that particular statement, that function TRID, because I wanted to see how that function looks like. Okay, then I go to the next cell and I can execute only that cell. Okay, when I execute this cell, it says S is set to 1, N is set to 4, but these are not printed because I put a semicolon, and then T equals tride Sn. So here I suppress the semicolon so that it will actually print out, and I get the output. And then here is a command called fprintf, which is a print command, and you can put any string within quotation mark. Okay, that will also be printed. And in this format specifier, you can put things like %G, which says use a generic format, and /n means go to the next line after you print that. And actually the function that calculates the determinant is this det capital T. Capital T is defined here. So it goes as an input argument, and det calculates the determinant and sends the result out. Okay, so it actually prints the determinant of matrix T is equal to. So if you see these strings are the ones that I place here. Okay, and then followed by the actual value, which is replaced. So I've executed the next set of cells, and I go to the next one and say execute this, and it says, okay, this is asking for LU factorization, so L is equal to and U is equal to. Here you notice that L is also lower triangular and U is an upper triangular matrix. LU factorization simply finds it in such a way that when you take the product of L and U, you get the T back. So you can separate each sections like this and produce a report very nicely. And if you go to the next section, here we are calculating the determinant of the lower triangular matrix, the determinant of the upper triangular matrix, and the product of the 2 determinants, which must be the same as the product of the original matrix T. So if you execute that part, execute this part, see the determinant of L is 1, because it has only 1s on the diagonal. The determinant of a lower triangular matrix is the product of all the diagonals. The same thing for upper triangular matrix. It's a product of all the diagonal elements. And the product of these two lower and upper triangular matrix is the same as the determinant of the original matrix that we saw. This you must have seen in the theory of linear algebra. We are just reaffirming that. And then we say, okay, go to the next cell. Here we are asked to calculate the inverse of T and inverse of L and inverse of U. Okay, so let's execute that. So you'll have inverse of L, which is also lower triangular, inverse of U, which is also upper triangular. Okay, and the inverse of T is a full matrix. Even though T is a tridiagonal matrix, inverse of T is a full matrix. And go to the next one. Here we are going to execute the rank. The rank is 4. The next one, execute that. These are the eigenvalues. Okay, so V is the eigenvector. Each column of V represents one eigenvector. There are 4 eigenvalues which are placed on the diagonal, and each column corresponds to the corresponding eigenvalue and the eigenvector. Now, it turns out that the product of the eigenvalues is also the determinant, and that is verified in the next statement. And the next statement, we are asked to verify that the eigenvectors are orthogonal. What that means is if you take the first vector and take the inner product with the second vector, they're perpendicular to each other. So the product will be 0. Similarly, first with third will be 0, first with fourth will be 0. But first with itself will be 1 if it is normalized. And we need to figure out a way of how to take these vectors and multiply in this particular fashion. And the simplest way turns out to be if you take the transpose of V and then take the matrix multiplication with V itself, that is equivalent to taking the inner product. So let's just see what happens. So there it is. Okay, so the first row with itself gives you 1, first row with second is 0, first row with third is 0, first row with fourth is 0, etc. So these eigenvectors are indeed orthogonal. The next one, you're asked to calculate the characteristic polynomial, and here is the characteristic polynomial using the function poly, which takes T as the matrix, and it gives you 5 numbers here, and these are the coefficients of the characteristic polynomial. And you can take the coefficient C1 and pass it to roots function to calculate what the roots are. And these are the roots, and if you compare this against the eigenvalues that we saw earlier in here, you'll find they are exactly the same values. In different order maybe, but they are exactly the 4 set of values. And this is how you can nicely demarcate various parts of the question into cells and execute them and make sure they produce a result. And once you have done that, you can say produce a report. So here, publish this report. And you can actually set what type of format you want. And here I've set it up as a PDF file. So it's going to produce a PDF file when I say run that. So it's going to run through the entire script, executing every one of them and produce a very nice report, which you can submit as part of your assignment. Let me just wait until the PDF file opens, and then we will close this particular part of the problem. There is your report produced by MATLAB. So this is an alternate way to using diary command, but it produces a very nicely formatted output, part A. But everything here basically comes from what you have put into your original script file. Okay, for example, we had part A and part B1, etc. Those are appear as title. And then below whatever appeared, like clear, type trigonal D, so those are echoed and the output is produced for you. Okay, and similarly the tridiagonal matrix and the L and the U factor and everything is produced nicely as a report, which you can submit. So it would be prudent for you to identify your uniqueness by putting your name, ID number, whatever you want to do that. So let's stop with that one. Okay, the second problem is about doing a process design type of analysis based on the model that we have developed for a stage-wise separation process. Okay, so here we have generalized from 3 stages to n stages. And once again, we have the inlet flow rate and composition for the liquid and the vapor that are specified in the problem. And you are asked to calculate all the exit liquid compositions and hence the vapor compositions from this equation, y equals kxi. Once you know x1, x2, xn, you can multiply it by k to get y1, y2, yn, etc. Now, The problem is linear as we saw earlier, and what we need to do is assemble the matrix T, which we know how to do from before, and assemble the right hand side, the forcing term B, which depends on all the input quantities. For example, it depends on S, but S is given by L over KV, and those numbers are given for us in this particular problem. K is given, L is given, V is given, and the two inlet compositions x0 and yn plus 1 are given here. Okay, so x0 is also given as we saw, yn plus 1 is given, and k is known. So the entire right hand side vector B can be calculated, and T can be calculated as we saw previously by making a call to the function TRID. Now specifically we are asked this particular case to do a case study, meaning solve the problem for different number of cases with different stages each time, n equal to 4, 6, 8, 10, and 12. And in each case you will get the composition from every tray, but we have to take only the exit composition y1. That is, in this figure, this composition that you see y1. And we need to plot that against the stage number. If I have 4 stages, what is the exit composition? If I have 6 stages, what is the exit composition, etc. Okay, so we need to run through the loop to calculate the exit composition for each one of those number of stages, 4, 6, 8, and 10. And then plot one against the other. And the second question is a qualitative one, asking which way is the material transfer taking place. The third one is, as n increases, does the exit concentration increase or decrease? Why? Once we plot that, we can answer that question. And the last part of this question is, when you have 12 stages, plot the stage-wise composition from stage to stage, just to see how the composition varies from stage to stage. How do we answer this particular question? We have a script file that we can write, and the script file including the cell structures I have used. So here is cell number 1, which just clears the workspace, cell number 2, which sets up the loop for n equal to 4 to 12. And here, if you notice, in line 7, I'm initializing all the values that are given to me. Here I'm using x0 as a scalar variable, which is 0, and ynp1 stands for yn plus 1. So again, a scalar value 0.8 that is given to me. And then I create a vector called yexit, which is a null vector. The reason I do that is every time I solve this problem for a particular value of n, I want to extract the exit composition and accumulate it in a vector so that I can plot that against the total number of stages that I have used. So the way it works is the following. If you want to understand that, I create a vector yexit as equal to a null vector. A null vector meaning it contains nothing. It's defined but contains nothing. Then I can say yexit is equal to yexit, comma 3, for example. So number 3 is added to that vector. So yexit now contains number 3. So if I do this, it takes the previous value of 3 and adds to that 5. And if I repeat that, for example, it takes the previous 2 values and adds the third value. So it continues to build that vector, each time adding 1 value to it. Of course, the idea is more powerful than that. You can do 15 to 17, for example. Okay, so you can add. But for our purposes, what you need to understand is I'm going to solve this problem. Every time I solve this problem through this loop, I'm going to extract the last exit concentration and add it to what was previously available so that I can use that vector for plotting here. Now, I want to illustrate how this loop works, so let me set up a breakpoint here and then start executing. Okay, so the execution has stopped at line 15 in the script, and if you notice what is the value of n, you will notice that it is 4. And of course you can look at the matrix T, you can look at the vector B, etc. But here is the solution, the composition from x1, x2, x3, x4 stages. But it is only x1 that I want, and take that and multiply it by k to get y1. So this is, product is y1. So I append that to the yexit, which is a null vector. So right now yexit is empty. But if I execute one time, now yexit will have 0.4129. Okay, that is the value that I just calculated as the exit composition when I have n equal to 4. Now if I continue this, the next time around it's going to be n equal to 6. And it will set up the matrix, it will solve, and it will extract the composition corresponding to n equal to 6 and add it to what you have before. Okay, now I have yexit containing 2 values. The first one is for the exit composition, when n equal to 4, and the second one is the exit composition when n equal to 6. When I continue this, it's going to do it now for n equal to 8, and the vector will have 3 numbers now. One is for n equal to 4, n equal to 6, and n equal to 8. These are the exit compositions, whereas the vector x contains the 8 stagewise compositions, x1, x2, x3, x4, when I have total number of stages of 8. Okay, I think you get the idea. So let's just remove that and then say, okay, continue to execute the rest. And it produces a figure, and this figure corresponds to the second part where we are actually plotting the composition against the number of trays. But the first part, of course, was overwritten. Okay, it was produced, but it was overwritten. Now, if I want to produce a report, I go to this icon and press the report, and it will create all the figures and put it into a nice PDF file, which will open up anytime soon. So here you have, this is for problem 2. Here is the line where from the script file where we initialized. Here is the loop, and here is the plot. The plot says that the exit composition decreases. That is, if you have more number of stages, the column gets more and more efficient, and so more of the material is transferred from the gas to the liquid. Okay, so the gas composition continues to decrease, and as n increases, the exit concentration in the gas decreases, as we saw in the graph above. The efficiency of the column increases with increasing number of stages. But for n greater than 7, the subsequent decrease is smaller and smaller and smaller. So it really doesn't pay to have a large number of stages, because the incremental decrease is getting smaller and smaller. Now, the second part of the question is, which direction is the material being transferred? It is transferred from gas to liquid, because the gas composition is the larger one, and it decreases with the number of stages. Now, the last part of the question is, for n equal to 12, plot the composition of both the liquid and the vapor. Okay, and how is it done in the script file? Script file, you notice that y is equal to kx. The last solution that came out of this is for n equal to 12. So x actually contains the liquid exit compositions for n equal to 12. So all you need to do is take that and multiply it by k to give you the y, and then you can plot from 1 to 12 on the x-axis. On the y-axis, plot the x composition with symbol O underlined, and also on the same graph, plot from 1 to 12 the gas composition with a symbol plus and a line. And that's what you would see in this graph, okay, x and y compositions. And the next part of the question is, it's called a stripper instead of an absorption column. So here the liquid has a high composition. If you go back to the problem, you'll notice that the liquid composition is 0.8. The gas entrant gas composition is 0. And we have only one case that we are going to study when n equal to 12. The k has been changed. It's a different system, and L and V are different as well. And so we need to solve it only for one case and plot the composition of xi and yi against the stage number. Okay, and that is done in the script file here. Set n equal to 12. Reconstruct your tridiagonal matrix, because your L, V, K are all changed. So you need to recalculate your S and use that S with n equal to 12 in here. And then also construct your B1 and Bn using the same S x naught yn plus 1 over k. And then solve for x, and y is k times x, and then plot x and y. Okay, and that's what produces this graph. This graph, concentration as a function of the stage number, okay, for the stripping case. Okay, and that's basically the end of the second problem.